Another one of the learning objectives for the carbohydrate chapter is to be able to describe the cyclic structures. Here I've got a monosaccharide, but you'll also want to be able to describe the structures of the disaccharides and the polysaccharides. We don't expect you to memorize these structures, but we'd like you to be able to describe them in terms of what units make them up and what kind of linkages they have. Here's the open chain structure of glucose, we call it. This is a typical carbohydrate. There are 6 carbons here. It's got an aldehyde at the top, so it would be an aldose. 6 carbons would be a hexose. This is an aldohexose. And we've numbered those carbons from the top to the bottom, starting with the end where the C double bond O is located, or as near as we can to where the C double bond O is located. The aldehyde group, as you know from the aldehyde chapter in organic, can react with alcohol groups. And what happens is that glucose, as it's twisting and turning and flexing bonds and so forth, this aldehyde group can react with the alcohol at position 5. And as it does so, then a cyclic structure would come together. Here I've redrawn the structure of glucose now. The CH2OH and the OHs have specific directions. If they did not, it would not be glucose. All of them have specific directions except here at position 1, which was originally this aldehyde carbon up here, because as the ring closes, the OH can be trapped in the up position, which is called beta, or it can be trapped in the down position, which is called alpha. So we've got 2 new glucoses, in a sense. They're both D-glucose, but we have beta D-glucose, OH up, and alpha D-glucose with the OH down. And one other thing I'd like to point out is that this position right here, that carbon number 1, where we had the aldehyde carbon originally, this is now a hemiacetal. It's got an OH. There's an H there that we haven't shown. The carbon is attached to 2 oxygens, and those are the requirements for a hemiacetal. So actually, if we were to look at a solution of glucose, what we'd find is that the open chain form is in equilibrium with these 2 cyclic forms, and the cyclic forms are opening and closing. So we really have a mixture of all 3. The ring forms predominate, but we'd have a little bit of this open chain form too. Let's look at a disaccharide. Maltose is malt sugar. It's comprised of 2 glucose units. And again, we don't expect you to memorize the structure of maltose to be able to draw it. But what we'd like you to know is that it's a glucose linked to a glucose, and in a specific way. They're linked by an alpha 1 to 4 linkage. Let's see if that makes sense. Here's position 1 of the glucose unit on the left. And remember, it can be up or down. And if it's down, it's alpha. And it's linked to the 4 position of the neighboring glucose unit. So it's an alpha 1 to 4. We didn't have to specify the direction at position 4, because if we say it's glucose, then it has to be down at position 4. We've got a hemiacetal group over there on the right-hand side, because it's got an OH and an O attached to this carbon. There's a hydrogen that we haven't shown. That hemiacetal group is opening and closing. Here I've shown it in the alpha position, but the beta position would exist too. So really there are 2 forms of maltose, alpha and beta maltose. This functional group back here on the left, well, here's our carbon. There's a hydrogen that we haven't shown. 2 oxygens attached to this carbon. It's an acetal. And acetals are a lot more stable than a hemiacetal. So this isn't breaking and opening. It's fixed right there. In carbohydrate chemistry, there's another name for an acetal group. It's called a glycoside. So this is an example of a glycoside, where sometimes we point to that specific bond, that carbon-oxygen bond, and call it a glycosidic linkage. Let's see, seemed like there was, I know there was one more thing I wanted to tell you, that when we take into our digestive system maltose, the body hydrolyzes this linkage and we get 2 glucose units. They're absorbed into the bloodstream at that point. Let's look at the structure of lactose. Lactose is also called milk sugar, and the 3 things that we'd like you to know are right here at the top. Its alternate name, the fact that it consists of 2 monosaccharide units, a galactose linked to a glucose, and they're linked by a beta 1 to 4 linkage. And when we take lactose into our body, the digestive system is able to cleave this bond, and we get a unit of galactose and a unit of glucose. These enter the bloodstream. Glucose, as you know, becomes blood sugar. Galactose enters the same kinds of reactions and eventually increases the blood glucose level as well. They're linked by a beta 1 to 4. Let's have a look. Here's a galactose unit on the left. It differs only at one position from glucose. Here at position 4, the OH is up rather than down. But at position 1, that's oxygen is pointing up, so it's beta at position 1, and it's down. It has to be down if this is a glucose unit. So it's beta 1 to 4 linkage. Here's an acetal or a glycoside over here on the left. Over on the right, with that OH, it's a hemiacetal. And rather than indicating alpha or beta, I used a wiggly line to represent that it's a mixture of the alpha and beta. Both are possible. So there are 2 forms of lactose. This ring is fixed, but this ring is opening and closing, opening and closing. Let's look at the structure of sucrose. Sucrose is household sugar. When we use the word sugar around the home, it's sucrose that we're referring to. If we use the word sugar in a clinical setting, of course, it would be glucose. The sugar in sugar beets is sucrose. Sugar cane is sucrose. Nectar in flowers is sucrose. Consists of a glucose linked to a fructose, an alpha 1 to a beta 2 linkage. So those are the 3 things that we're concerned about right there. We'll look at the structure, but again, you don't have to worry about being able to reproduce this structure. Here's a glucose unit at the top. Here at position 1, it's alpha. Down at the bottom is the fructose ring system, a 5-membered ring rather than 6. This is pyranose, this is furanose. This is position 2. It goes 1, 2, and then works our way around the ring. Up here we have an acetal linkage. Here we have a ketal, and neither one of these are hemi. So there's only one form of sucrose. It's not opening and closing to an aldehyde form. And so sucrose, when you talk about the reactions of disaccharides, it's not a reducing sugar because the ring form just stays that way. There's no open chain form. In the 8th minute of this video, I misspoke. When we were looking at this structure, I called it a triose. And it obviously has 4 carbons. That would make it a tetrose. So don't let my mistake mislead you in this video. Thank you.